sort of covered the integration stuff we need to cover. We've done a little with probability. So sort of covered the mandatory material. I mean, even probability wasn't mandatory material. I sometimes cover it and sometimes I don't. So let's talk a little about differential equations. And this is in the textbook and not going off book. It's just that we often don't end up having time to solve it. We seem to have moved pretty quickly this semester. Since people did well on the test, I'm fine with that. I don't see any indication that we should have moved slower. So this is a little the way sort of derivatives are presented. It's a little surprising. But in the real world, derivatives are often easy. Well, let's call it the actual function is hard. And I mean, we can see this even in things like position, velocity, and acceleration. Even in that sort of classic example, velocity on near the Earth's surface, velocity is a constant. Velocity, not what am I saying? Acceleration is a constant. Acceleration is easy to measure. Whereas if somebody's walking, if I throw that up and I say, well, what's a formula for its velocity? What's a formula for its position? I mean, it's pretty clear that that is not easy to measure. I mean, as technology improves, we could, take 1,000 photographs of the pen, and we could use those to create a graph, and we could recognize that the graph is a parabola, and we could do polynomial regression to figure out what the parabola is. But just in terms of looking at that and writing down a formula, it's a lot harder than measuring the acceleration is. Like similarly, say this is my artist's rendition of a stream. We've got rocks, we've got a branch sticking out. Measuring the derivative of water current is really easy. There are little custom-made tools you buy for the job, and you stick them into the water, and it tells you how fast the water is moving and what direction the water is moving in. And this is really calculus 3 stuff because we're in more than one dimension, but that is the derivative. What's not easy is creating a function, call it f of x comma t, that will take x as a starting position and then predict exactly where a little boat that you release from here will be after t seconds. In fact, I'll go so far as to say that it's basically impossible to do that. So, again, measuring the derivative is easy. Talking about the original formula, maybe functionally impossible. So that brings us to differential equations. And a differential equation occurs when you have info about a derivative and want info about the original function. And you might look at that sentence and you might say, oh, so anti-differentiation. Differential equations is therefore the study of antiderivatives, because antiderivatives are how we go from a derivative to the original function. But only on the most rudimentary level is differential equations the study of an antiderivative. Because a lot of times a differential equation will end up looking something like this. The derivative of y with respect to x involves both x and y. And if you try to resolve this using integrals, maybe it's instructive to compare it to dy dx just equals x. Certainly, in both of these cases, we can integrate both sides. The fundamental theorem of calculus, the first part of the fundamental theorem of calculus, the part that we haven't been using, but which I promised was important. The first part of the fundamental theorem of calculus says that the integral and the derivative undo one another, in the sense that if you differentiate with respect to x and then integrate with respect to x, you end up with the original function. You end up with y. So you see what's happened if we compare these cases. On the right, we were able to just do everything. We integrated x, we got 1/2 x squared, y is 1/2 x squared plus c. Here, we got this horrible bit of recursion. Y is defined in terms of the integral of itself. Y is defined in terms of the integral of y. we can't compute this integral if we don't know what y is, but we can't know what y is until we compute this integral. So this differential equation is not amenable to integration. We need other tools to study this. And Math 330, this is an entire dedicated class to studying differential equations. Most of Math 330 is based around linear algebra, around matrices. So, of course, we're only going to present a very rudimentary introduction in this class, but first, let's make sure we're all on the same page here. A solution to a differential equation is a function that satisfies it. And just to make this very correct, I'll write on some interval. I don't know if that's really going to come up in this brief introduction, but functions can have vertical asymptotes, and if a function isn't defined somewhere, it's certainly not satisfying an equation at that point. So we clarify, and likewise, it's not enough to do it at a single point. We want something substantial here. So, for example, having given this definition, sometimes even textbook authors who ought to know better, will say that the goal of differential equations is to find solutions to differential equations. And, if they're doing a lot of numeric work, that might be true. You can numerically estimate solutions of differential equations. But most real world DiffEQ, the standard differential equation abbreviation, most real-world DiffEQs will not have closed form solutions. So today and tomorrow, we're going to look at some differential equations that do have closed form solutions. And then Wednesday, we'll get to talking about, well, how can we study these if they don't have closed form solutions? And Thursday, I am not planning to meet, because, as I say, we're already in the cultural enrichment, isn't in the syllabus section, so I think that's appropriate. So I just want to state this, even though at least 2 of the days of this week we'll spend looking at solving differential equations, what we really want is more general and hard to state formally, we want to get info about a solution. And we'll see on Wednesday that you can sometimes get very important information about a solution without actually solving anything. And a big one is horizontal asymptotes. You can very often ask, well, what happens as time goes to infinity? And answer that question without actually solving the differential equation. With these disclaimers out of the way, we'll present a solution technique. Separation of variables. So we are told again and again and again that when we see these dy's and dx's, they're not real physical objects. When we see, for example, dy dx equals x times y, that is not a fraction we can manipulate. We cannot, so we tell students, multiply both sides of the equation by dx, because this is just a bit of notation that represents the derivative of y with respect to x. It's not an actual fraction. Having said that, we have if we pretend that it is a fraction, we have a pretty good hit rate of getting useful results. Like when we present the chain rule for the first time, this version of the chain rule, our students, I told you, well, these aren't fractions, properly speaking, but if they were fractions, this would just be tautologically true, because those dx's would cancel, and this would just be the statement that dy dt equals dy dt. This would be just a true statement, a tautology. So even though we're not supposed to think of these as fractions, it's helpful to think of these as fractions. Separation of variables asks, well, what happens if we treat the dy and the dx as a fraction? What happens, where is it? If I take dy dx equals xy, and I pretended that dy dx was a fraction, and I got all the x's on one side of the equality and all the y's on the other. Called separation of variables because we are taking our variables and we're separating them. X is on one side, y on the other. Good. Well, we can do. I mean, I say we can do that with the understanding that we're actually doing something kind of weird here, and that dy dx isn't really a fraction. But if it were, we could do this. We would end up with 1 over y dy equals x dx. Remember what happened when we tried to solve this with integrals? We threw integral signs on both sides, but we ended up with an integral that we couldn't take. Whereas now, if we add integral signs to both sides, the integral of 1 over y dy equals the integral of x dx. And the issue that we had our variables mixed together inside of integrals vanished. We've got an integral of y's, we've got an integral of x's. What's the integral of 1 over y dy? The natural log, exactly correct. Thank you. I'll put the plus c, although that won't stick around. What's the integral of x?
1/2.
Yeah. So the reason I said the c wouldn't stick around is now we can subtract it from both sides. And if d is a totally arbitrary constant and c is a totally arbitrary constant, so is d minus c a totally arbitrary constant. So when we do this, we just write down a single constant of integration. Now, if our goal is to solve for y, those absolute values are going to be a bit of a nuisance, but how do we get rid of the natural log?
Exponentiate.
Exponentiate. Oh, I act as if I'm cramped for space when in fact I have an unlimited amount of space. One half x squared, and seem to have slipped into sort of computer science notation briefly. I don't know why, it was sort of unconscious. On the left, the exponential and the natural log cancel each other out. On the right, especially because we're definitely not used to looking at this and asking how this simplifies. But on the right, we have addition in the exponent and addition in the exponent. Oopsie. Addition in the exponent can be rewritten as multiplication. So The statement is now a little mushy. Yeah. In the sense that there's no proper way of getting rid of of absolute value. So we have a statement about the absolute value of y. Fortunately, differential equations is a field of applied math. So we don't just have to flail around. We can make some assumptions. And in probably 999 times out of 1,000, y is a positive constant. Y is population. Y is dollars spent. Y is troop size. Y is the number of sick people. So if we just assume that y is positive, we can also, sort of similar to that constant of integration minus a constant of integration, e to a constant is a constant. And we have successfully solved for y. And that is separation of variables. And now you might be thinking, okay, so differential equations is just antiderivatives with a few extra steps thrown in at the beginning. But separation of variables is not a cure-all. It is not a universal method because it's very easy to write down differential equations where you can't separate the variables. I mean, just something like the sine of or dy dx equals x squared. I mean, this is a differential equation. The derivative is stuck in the sign. You can't get at it. And you know, if you're thinking inverse trig functions, remember that when you use the inverse trig functions, you're suddenly imposing restrictions. The arcsine and the sine will cancel out if dy over dx is between negative pi over 2 and positive pi over 2, but there's no reason it should. So you can't just use the arcsine, and you cannot proceed with separation of variables. Let's do a simple but important separation of variables problem. Simpler, in fact, than the one I started out with, but more important. Dy dx equals a constant times y. So this differential equation shows up all the time because this differential equation is saying that the rate that y grows at depends on what y is right now. And this shows up, for example, if we're looking at the spread of a disease, the spread specifically of an infectious disease. So in disease dynamics, in virology, let's say disease dynamics, because I'm not convinced of that word. Every disease has a number attached to it. The basic reproductive ratio. And that is answering the question, if someone gets sick, how many people will they make sick in her? Not a parenthesis, but a quotation. So let's say R equals 3. And we ask, how is this disease spreading? At what rate are people getting sick? Well, there are currently Y sick people, and the rate it is spreading at is 3 times the number of currently sick people. If there are currently 10 sick people, then tomorrow we expect an additional 30 sick people. So the rate that this is increasing is 3 times the current rate. And this is precisely what we have over here with k equal to 3. And there are other very standard applications, like it's if you think of the spread of a rumor, it's appropriate that the spread of a rumor can be modeled as if it were a disease. You ask, well, how many people do we think, I've heard the rumor, I'll tell it to 2 other people, dy dx equals 2 times y. Elementary population dynamics. How many animals do we think a pregnant female will give birth to? Or we could ask how many female offspring specifically. The more female animals there are giving birth, the quicker the animal population increases. And this is, nope. Just for a little context, in differential equations, you commonly sort of swap things out. You use x instead of y as the dependent variable, and then you use t as the independent variable. So the reason you keep seeing me make that specific mistake is that I'm not doing that in this class. I'm using x's and y's. So this is separable, just like the previous example was. It's, in fact, simpler than the previous example, in the sense that when you integrate, there are no variables on the right at all. We just have k. Simple or not, I made a mistake. This dy is sticking around on the left. I hope it's not confusing. I'm doing two steps at once. I'm dividing the y over to the left, and I'm multiplying the dx over to the right. And now we chuck those integral signs on. We get the natural log of the absolute value of y equals k times x plus c. Exponentiate both sides. Once again, e to the c is a constant. We'll just write the number there. Once again, we have an absolute value. And here, I mean, it might have just looked like, well, Dr. Moses doesn't know what to do, so he's making this fake assumption. But I mean, here, if we're looking at the spread of the disease, y does have to be positive. If we're looking at the spread of an animal population, the number of animals does have to be positive. If we're looking at the spread of a rumor, the number of people who have heard the rumor does have to be positive. So we can just get rid of the absolute value. And in differential equations, you're always, always, always assuming that every constant is positive. If you wanted a negative sign here in a differential equations class, you would manually put one in so that we can keep assuming that k is positive. And if you, let me now undo that, I don't actually want those. You see, if we assume a is positive, then this is a positive number times a positive number. Y is positive anyway, and the absolute values wouldn't do anything, even if we left them in. So that's separation of variables. I mentioned animal populations. Separation of variables applied to a fairly rudimentary but still robust population differential equations will give us a separable differential equation that can be solved using partial fraction decomposition. So it's nice to see these techniques that we've learned actually used for something. So tomorrow we'll talk about population differential equations. Then Wednesday we'll talk about fixed points, a method we can try to use sometimes if we can't solve the thing. And I will see you then.